Hello, everyone. Welcome to the 7th episode of High School Math Fundamentals here. Today we're going to start into some calculus here. These next videos are going to be on calculus here. And this is about derivative rules here. Okay, so let me just go over what a derivative is again. Right, just for reiteration, it doesn't hurt. Right? Say we have a function here, and it looks like this. Okay. What our derivative? Say this is f of x, right? And our derivative here would look something like this. Or like this. That's a better drawing. Right, that's f primed at x. Right. It's not exactly what it's gonna look like, but yeah. So it represents the slope of the tangent lines across all across this first line here. So you notice that beginning, the slopes of the tangents are very high. The lines are very steep of the tangents. So our derivative function starts off really high up here, right? And then it's going to become 0 here. We have a 0 in our first derivative here. And then somewhere around here, we're going to have a point of inflection. So those correspond to zeros in our second derivative, which I'll get into later. And it's decreasing along this interval, so you'll notice that the slopes are negative, and that's reflected here, right? And again, up here, we have positive slopes. Positive slopes, and they get steeper and steeper and steeper. That's reflected in the magnitude of, or the value of our first derivative function here. Okay? All right, so get rid of that. Let's get into the sum difference rule. Actually, before I get into that, I'm just going to state the power rule again. Okay, so power rule. We have, let's say we have f of x equals x squared, right? Our derivative here, f primed at x, we're just going to imagine that 2 hopping down as a coefficient in front, and that exponent being 1 less than it was before. Okay, so our derivative would be 2x. Okay, similarly, if we had f of x here equals root x, right? That's like saying x to the power of a half. So you take that exponent, bring it down to the front, and subtract 1 from that exponent there. So this is f primed at x, and that's the power of negative a half, right? Or you could say 1 over 2 root x. Let me just move this down. Okay. So let's get into sum difference rule here. Sum difference rule just states that if f at x, or I'll say h of x actually, equals f of x plus g of x, right? Those are 3 distinct functions. The derivative of the function h primed at x is going to be pretty simple, just f primed at x plus g primed at x. And similarly for differences, it's just going to be a subtraction sign here. And you can have as many f of x, g of x, d of x, like you can add as many as you want together. This rule will still apply. Right, so let me just change this here. They're the same. Let me just get a quick example here. or I'll say f of x now. F of x equals 5x cubed plus x plus 7. Okay, our first derivative then is going to be that 3 goes in front there, multiplies with the 5, 15x squared plus 1 plus 0, or just plus nothing there, because our 7 here turns into a 0 when we differentiate it once, and our x will just turn into 1 because this is like x to the exponent 1. We move the 1 to the front, and it becomes 1 times x to the 0, and x to the 0 is just 1, so okay, perfect. Now let's move on to product rule. So the product rule states hx equals f at x gx. So you have two functions multiplied together here. You are going to get as h primed at x, you are going to have f at x, or f primed at x, times g at x plus f at x g primed at x. Okay, and a nice way I like to remember this is this is the right d left, and then left d right, with the d meaning a derivative here. So right d left, left d right. Okay, so that's product rule, and applying it now, let's say f of x is equal to 5x multiplied by, let's say, 1 over x squared, or no, I won't do that actually. I'll just say 5x multiplied by root x. Okay. In this case, it might just be easier to kind of simplify these, but I'll just show it to you to show that the product rule works. This is not by any means the easiest way to solve this problem, but so we can turn 5x using the thing here, the formula, into its derivative. So that's now 5. The derivative of root x we found before, it's 1 over 2 root x. Yeah, 1 over 2 root x. So that's multiplied by 1 over 2 root. Actually, no, not yet. It's just the thing here. I was getting ahead of myself. It's just a g of x, not g primed at x yet. And then f at x, again, so that's just 5x. Then g primed at x, this is g of x. G primed at x now is 1 over 2 root x. Okay. So we can simplify this now. 5 root x plus 5x over 2 root x. You can get a common factor here of 2 root x, I suppose. 2 root x plus 5x all over 2 root x. Okay. So 5 root x multiplied by 2 root x is 10x plus 5x all over 2 root x. That's 15x over 2 root x. This is 15 over 2 x over root x. X over root x is just root x, so that's 15 over 2 root x. Okay. So if we want to see that in other terms here, we can just simplify this to 5x times root x is like saying 5x times x to the power of a half. And by one of our exponent laws here, when we're multiplying them, the exponents will add. So that becomes 5x to the 3 halves, right? And now differentiating this is, just use the product rule here. Sorry, power rule. That's x, subtract 1 to the 1/2, 15 over 2. And that's just root x. Okay. And that's what we got down here as well. Okay. So let's get onto the quotient rule now. Okay. So if we have h x here equals f at x over g at x, our derivative is going to be, let's see if I can remember this correctly, f primed at x times g at x minus f at x g primed at x all over g of x all squared. Okay, let me just confirm that. Yeah, that's correct. Okay. So let me get into an example here now. Let's say we have y is equal to 4x minus 3 over 2 minus x cubed. Okay, the product rule might have been better to use an example like this too. So y here, y primed, it's going to be 4x minus 3. The derivative of that, we're going to kind of combine the sum difference rule here, but this is just going to be 0, right? Because the derivative of a constant is 0. That's just a known thing. Because the graph of a constant, say it was x equals 3, that'd be like this, just a line like that. The slope of that line is always 0, right? So our derivative is always going to be 0, no matter what, for that function, x equals 3. Okay. So let's differentiate this guy now. So 4x minus 3 is like our f of x, and 2 minus x cubed is like our g of x, right? So our derivative of the numerator here, that's just 4, right? Because by power rule and sum difference, right? And then we're just going to write our denominator here. Oops. Kind of broke there for a moment. Okay. And then we're going to subtract 4x minus 3. That's just the original f at x there. And we're going to multiply it by the derivative of the denominator. So in that case, it would be 0 minus 3x squared. So just minus 3x squared, or negative 3x squared. Okay, and that's all over 2 minus x cubed all squared. Okay, and now we can simplify this now. Depending on your teacher, you might not have to simplify it. They just want to know that you can apply this formula properly, but I like to simplify it because you can get this in a little bit of a simpler way here. So let's expand this first term in the numerator here. We're going to make it 8 minus 4x cubed. Okay, and that's all minus, let's just expand this too, negative 12 x cubed, right? And then we're subtracting, or we're going to add now 9x squared. Okay. All right. So that's our numerator. And our denominator, I guess we should just leave it as it is. Okay. So now this numerator can become 8 minus 4x cubed plus 12x cubed and minus 9x squared all over 2 minus x cubed squared. And okay, so we're gonna have 8 plus 8x cubed minus 9x squared all over 2 minus x cubed. Okay, so that's going to be our derivative there, our first derivative. We could apply the quotient rule again and get our second derivative, but that'd be a little bit of work. Okay, and I guess let's do this example using, or I'll do the chain rule first and then I'll go back to this one. So chain rule. Okay, this one's usually the hardest to grasp for most students, I find. And I know it was a little confusing when I first looked at it as well. So the chain rule is like, you know, regarding multiple functions here, right? So if we have like composite functions, we have h at x is equal to f at g of x. It's like when we have a function inside of a function, right? So what the chain rule states pretty much is that the derivative is going to be just like exactly what you see here, just with f primed at g of x, right? And then that's all multiplied by the derivative of the inside here, or g primed of x. Okay, if that makes sense, right? So let me get into an example here. Okay, so I guess we'll go back to using the product rule right now. Let's say we have a function f at x here, and it's 8x minus 3 to the fourth, all to the fourth, multiplied by 3x squared plus 5 all to the 7th power. Okay, so for this one we're going to have to use the product and the chain rule, but I'll tell you when I'm applying both of them. So let's do f prime at x here. Or instead of f prime at x, you could also write d by dx. You could use the Leibniz notation here of f at x. Okay, either way, it still just means the derivative, right? So this, we're gonna try using the product rule here. The product rule states, you know, that right d left, left d right. Right. So our derivative of this, using the chain rule now, the 4 is gonna kind of hop out here and go in front, right? Because we're finding the derivative of the outer function. Like say 8x plus 3, or sorry, minus 3 equals u here, right? We can say that. And so this expression here that I'm underlining, it's kind of just like saying u to the fourth, right? And if we want to find d by du of u to the fourth, that's just 4u to the third, right? So, but you still have to find the derivative of this, right? So it'd be u primed here, but don't have to worry about that. Okay, so or we are going to have to worry about that because we'll do it in a second, but let me just write this out here. So it's going to be 4 times 8x minus 3. Remember, it stays the same on the inside, and that's also the third power because it would be 4u to the third. And then you got to multiply it by the derivative of this, and that's just 8. 8 minus 0, but just 8, right? And then we got to multiply that by just the regular version of g of x here, which is 3x squared plus 5 all to the 7th. And that's plus, since we're using the product rule now, right? Just the f at x, so that's just the regular 8x minus 3 to the 4th here. And we find the derivative of this now. So that is 7 times 3x squared plus 5 all to the 6th. Right? And then the derivative of this inside now, this is going to be 0, and this is going to be, the 2 is going to go in front, and it's going to be 6x, right? Because you also subtract 1 from the power. Okay, so 6x. Okay, right, so now that we have this mess here, we're going to try and make it a little bit simpler. So I'm going to multiply the 4 and the 8 here to get 32. I'm going to have 8x minus 3 all to the 3rd, 3x squared plus 5 all to the 7th. And then I guess I'll multiply the 7 and the 6x here. So 7 times 6 is 42, and x, 42x, right? 8x minus 3 all to the 4th, 3x squared plus 5 to the 6th. Okay? And now out of this full thing, we can factor out common, what's the greatest common factor between 32 and 42? If I'm not mistaken, should be just 2. Yeah, I think it should be just 2. Okay. So, and we have common factors of 8x minus 3 and 3x squared plus 5 here. So we can factor everything out. Not everything, but everything from each one of these kind of individual guys here. Right? Does that make sense? So we can factor out 8, we said. And since this is bigger by 1, right? We have 8x minus 3 to the 4th and 8x minus 3 to the 3rd. We can't factor 8. Well, I mean, we can factor out 8x minus 3 to the 4th. We just get a fraction, but we're going to factor out this 8x minus 3 to the 3rd. Right? And then here, this is lower here. We're going to factor out the 3x squared plus 5 to the 6th. All to the 6th. And in the brackets now, 32 divided by 2 is 16 here. Right? 8x minus 3 to the 3rd divided by the same thing is just 1, and multiplying by 1. I don't even need to write that down, actually. And then 3x squared plus 5 all to the 7th divided by 3x squared plus 5 all to the 6th, because that's what we factored out, remember? That's why I'm dividing it by it. It's just one copy of it. Because if you have n to the 7 over n to the 6th, your answer is just n, right? By the quotient law of exponents. You just subtract them, right? So 3x squared plus 5. Let me get the regular color here. 3x squared plus 5, and that's it. Then we still have plus 21x, and then we're still going to have 8x minus 3. And then that will just, it's dividing by itself, so just leave it at that there. Right? And you could now distribute these both and then collect your like terms, but that's pretty straightforward. I don't think I have to go over that. Okay? And sometimes you won't be required to simplify. Depends on your teacher. Okay? You can go further with this, though, and make it more simple. So Okay, so that's the derivative rules, pretty much. I guess I'll just touch on maybe a word problem here. Okay, let's do a quick optimization problem here. Okay, using first derivatives. Okay, we are going to have a cone here. If I can draw it nice enough here. It's going to have a base like that. Dotted line inside. With that height. There's a right triangle inside of it here. And then we're going to have a cylinder inside of it. Right, it's going to look something like this. It's inscribed inside of it. So we want to find out now, what is the maximum size of the cylinder that we can inscribe into this specific cone here? Or what is the maximum volume, I should say, of this cylinder that we can inscribe into this cone here? And I'll make up some dimensions here. Its height, let's say 30 centimeters. The diameter of the cone, we'll say is 20 centimeters, right? And so half of it, which is the radius of the base of the cone, is 10 centimeters. Okay. Don't mind this messy drawing, but notice this cylinder also has a height and a radius too. Right, so that's little r and h, we'll call that. You would have to put like let r, h represent radius and height of the cylinder. Okay. So we know that the formula for the area of this cylinder is going to be V is equal to pi r squared. That's like the area of the base of the cylinder. And we're just going to multiply that by the height to find the volume. So we do for most prisms. Our cylinder is not really a prism, but the same logic would apply to prisms. Okay, pi r squared times h. Right, that's the volume of that cylinder. Okay, so what we can do now, we have two variables here. We can't differentiate in terms of two variables here. So what we're gonna do is try and get it in terms of one variable. Okay, so notice in this this bigger cone here, we have like a triangle here, right? And then there's like a smaller triangle within that triangle of just the, like representing the height here and the radius of the smaller cylinder. And then in the bigger one, it's the height of the cone and the radius of the cone. Okay, so let me just draw those two triangles out side of the diagram here. So that's the triangle, the bigger triangle. And they're right triangles, by the way, because the height and the radius are perpendicular. And then the smaller one is kind of inside of it here. It shows a right angle, right? This is h, this is r, because we defined it, right? And since we know the whole height is 30, we know this little segment here is 30 minus h, right? And we know also, or I suppose I'll put r up here. This is also r here. And so the similar triangles there. Okay, and we know they're similar now because they share an angle here and another angle, the 90 degrees, right? So if all angles are the same in two triangles, they're similar. Okay, so by this logic now, we can set up a kind of ratio here. Oh, and the bottom of this, bottom of this is 10 centimeters, and then the side of this is 30 centimeters for the height and the radius of the bigger cone. Right, so we can say now that since they're similar triangles, 30 over 10, which is just the ratio between the height and the radius of the cone there, is actually equal to, so going by the same logic here, we have 30 corresponding to our 30 minus h here, because they're similar triangles. We can equate these ratios. So we can write 30 minus h on the top here, the numerator. And we have this r corresponding to the 10 centimeters. Okay, so we can write that in our denominator now. R. Sorry, let me try again. Okay, R in pink this time. Okay, so now we can isolate for r by cross multiplication here. Let's simplify this other side though first to 3, because 30 over 10 is just 3. 30 minus h over r. Okay, let's cross multiply now. So 3r equals 30 minus h. Dividing both sides by 3 now, we get r is equal to 30 minus h over 3. Okay, so that's r. Now we can sub that into our original equation here. V equals pi. Now we know r to be 30 minus h over 3 all squared times h. Right? So you may be asking now, what are we supposed to do with this, right? But you might find it helpful, or you would have to do it this way, to just kind of differentiate in terms of h, with respect to h, I should say, right? Because our derivative, we can picture this height changing, the height of the cylinder going up and down, right? When it's at the very top, the volume is going to be very small. And so, and the same with the bottom, with a very low h, right? It's going to be very low to the ground and have next to no volume. We're going to have a sweet spot right in the middle, like kind of how I drew the diagram. It's not going to be exactly there, but you get the idea. We can change h so that the volume of the cylinder inscribed in this cone here will have the maximum volume. We're essentially optimized. This is an optimization problem. I'll write that down actually. Or we can call it a maximum minimum value problem. Okay. So we can picture this as like a function now, right? And say the function, it doesn't look like this, but say it's like this. Whoops. We're actually also going to have to set restrictions. We have to say that h belongs to the closed interval 0 and 30, right? Because it can't be bigger, or else it's outside of the cube or the cone. It can't be smaller than 0, or else it's going like underneath it, right? So we can picture this as a function, right? And say the graph of this function looks like this. It doesn't, but say this is our domain here, right? We're gonna have a maximum value, right? So that maximum value is gonna correspond to the like the maximum value of this this original function, right? If we find the first derivative, right? And we're going to want to look for zeros in our first derivative, right? Because what do we notice? It's flat. The tangent line to this is flat at that point, okay? And same down here. But we'll distinguish between maximum and minimums in a second here. Let's just find the derivative first. Okay, so by product rule here, we can use this is the f of x, and then this is the g of x. So we're going to find the derivative of this pink one here first. So it's going to be 2 pi, right? And then multiplied by 30 minus h over 3. And if you think about it, the inside is kind of like 30 over 3 minus h over 3, right? And that's just going to be 0 when we differentiate it. But this h over 3 is going to turn into negative 1 over 3, right? Because it's like negative 1 over 3 times h. And using the power rule, we're going to get just negative 1 over 3 as our answer here. So we're just going to multiply it by negative 1 over 3. And of course, that's now multiplied by just h, which is the g here. Okay, so that's the first term in our power rule, applying the power rule. And then the derivative of this is just going to be 1, so we don't have to write it. I'm just going to write this first bit, which is f of x. All squared. Okay, and let's simplify this now. We will say, let's factor out a pi first, right? Okay, and then inside the brackets, let's just multiply this 2 by this negative 1/3 right off the bat here. So we're going to get negative 2 over 3, right? And that's multiplied by 30 minus h over 3. Actually, that's a common factor too, so let's pull it out at the very beginning. This is a common factor between both terms since we have it here and here, right? We actually have 2 of them here, but we're just going to pull out one of them. Okay, so we're going to pull out a pi and a 30 minus h over 3, right? And then left we have this 2 times the negative 1/3 here, so that's negative 2/3, right? And then of course we have over here now, oh, whoops, on this side we just have plus 30 minus h over 3. Sorry, I missed something here. That's actually going to be multiplied by h, because we did not factor out that h initially. Okay. So that's our first derivative. And since we're looking for when it's 0 to find the maximum or minimum values, we're going to find our zeros of our first derivative here. So set it equals 0. All right, that's 2h over 3. And actually, we can add 30 minus h. That's all over 3. And actually, let's simplify this even further now. So this is h plus 30. Negative 3. Yeah, sorry. negative 3h. Okay, so now we can have you, we can ignore this pi. We can say that 0 is equal to this, or 0 is equal to this, right? So we have 30 minus h over 3. We also have 0 is equal to negative 3, negative of negative 3h. Or let's not, we're not writing this here. Okay, so it's just negative 3h. Sorry, I messed up earlier, but this is how it is. 30 over 3. Okay, so we have these two solutions to this equation now. Let's actually go ahead and find these zeros. Multiply both sides by 3 here. It's just going to be 0 times 3 is 0. And then add h to both sides. So h is 30. And then over here, we are going to have multiplication by 3 on both sides again. So it's just going to be 0 times 3 is 0. And then, so 0 equals negative 3h plus 30. We can add 3h on both sides. And then divide by 3 on both sides, so h equals 10. Okay, so we have two solutions. H is 30 and h is 10. Okay, and we know that most likely this is going to correspond to a minimum value here. Okay, because we said that 30 is kind of when this will be 0 up here. Okay, the volume is going to be 0 if we punch that in, right? Because it'd be 30 minus 30 over 3. This is 0 over 3, and that's all squared, right? So, yeah, our answer is the height is 10. And if we want to find the maximum volume, just plug this function in. Sorry, plug h equals 10. I don't know why that's 0 now. H equals 10 back into your original function here to actually get the volume. Or you can do it into this one, actually, sorry, since you don't have R. Okay? That's it for this episode. It was a lengthy one again, but thank you for listening. Catch you later.